Okay. Alright, so this is a video lecture. It's going to be on rate law basics and finding the rate law from data. I'm trying this new format right now, so let me know tomorrow if this is better or worse than what you had last time. Alright, so this is the lecture on chemical kinetics. We're continuing with that. Today we're going to be covering rate laws, basically the basics of it, and then how to find it from data. This is a little bit different from what I did last week, which was do it live in front of you guys during our club meeting. So let me know tomorrow if this is better or worse than what you guys had last week, which one you prefer. Alright, so I want to start with a review question. Go ahead and read that and pause it and answer it before continuing on. Yeah, so the answer here is D. Alternate reaction pathways become available at higher temperatures. That doesn't happen. This is a question from a practice AP test, if you guys were wondering. I also had a couple of more practice questions on the video, like the slideshow from last week. If you haven't already, go to the slideshow from last week, like the actual slideshow, not the video, and try the problems in there. They're going to be at the very end, and the answers are in the description or the speaker notes. Yeah, and then just to recap what we did last time, rate of reaction, we covered how to get the rate of reaction as an average of 2 points, which is an approximation. And then we have the rate of reaction as an instantaneous rate of change, woo calculus. And then today we're going to be looking at how you can find the exact rate of change from the concentrations of the reactants at any given time. And the way you do that is by using the rate law. So in general, like the general form of a rate law is rate is equal to K, concentration of A to the power of M times the concentration of B to the power of N for the reaction seen, like the general reaction seen there below. In class, we tend to use this kind of cursive K instead of just a regular print K. So you'll see Ms. Diva use that later on in the year, and I encourage you to use it as well. The reason we do it that way is in order to differentiate between the K that we use for equilibrium. This one is a lowercase k, and the equilibrium is a uppercase K, but it still looks too similar, so we use cursive. And then just so you know, K changes with temperature, and it determines how the temperature changes the rate. Remember last time we discussed temperature as one of the factors of rate. Note that this law only works for gaseous and aqueous reactions. You will never be asked about two solids reacting, except to show that the rate increases as the surface area of the solids also increases. If a solid is one or more of the reactants in a reaction with a solution, the solid just does not factor into the rate law. So for example, if in the above reaction on the screen here, B was a solid, the rate law would be rate is equal to K times the concentration of A to the power of M. M and N are typically small whole numbers, but they might also be fractions or decimals. They are based on the coefficients of A and B, if and only if the reaction occurs in one step. We will cover that more in like 2 presentations from now. Note that there's a difference between rate law and specific rate law. Rate law is going to have the K in it, and then specific rate law is going to have a number for K instead of the variable in there. A specific rate law will always be connected to a certain temperature because that's what determines the K. So this is a favorite question type for both the AP multiple choice and free response and for Chem Olympiad. I encourage you to take a picture of the slide so you can reference it later. And this is how you're going to be finding rate law from the initial rate data. So you can see the initial concentrations, in this case of ammonium and nitrite, and then the observed initial rate in molarity per second. Again, rate is always going to be in terms of molarity per second, so capital M divided by S, or some other unit of time. Yeah. Well, should probably cut that part. So the first step to solving is to solve for M and N. The method here is to choose two different trials from the list you have, where one of the reactants has the same concentration while the other one changes. For example, in experiments 1 and 2, the nitrite concentration is 0.200 moles per liter, while the concentration of ammonium changes. You can see that in the data that I pasted in there. And then by comparing these two experiments, you can find M and N. So I'm going to run through with you guys how you find M, and then I'm going to let you guys do N on your own. So we're going to take the first two experiments where B, so remember M is connected to A, and then M is connected to A, and N is connected to B. So we're going to find the one that B is constant. And I put in there experiments 1 and 2, so you can see the data in there. We're going to place the two experiments over each other, basically as a fraction. So here you have the rate of the first experiment is equal to K times the whole rate law, and the same thing for the second reaction below. And then we can input the values from the experiments. So in this case, you have 5.4 times 10 to the power of negative 7 is equal to K times the concentration of A, so 0.0100 moles per liter, to the power of M. We're going to leave those in there, and then 0.200 to the power of N. And that's for the first one, and then you're going to do the same thing for the second trial there. And then from here, you can see you can cancel out a few of the constant values. So in this case, we have K. K is always going to be constant, and you can always cross that one out. And then you also have, in this case, the concentration of B, or nitrite in this case, which is 0.200 to the power of N. So you can cross that whole thing out. From there, what you're going to do is you have, well, here's what's left first off at the top there. And then from there, you can simplify. So you can see all the steps in there. If you're confused, I encourage you to pause and look through that entire thing. But basically what you're getting here is you end up with 5.4 divided by 10.8 is equal to 1/2 to the power of M. And then from here, you can simplify that even further to 1/2 is equal to 1/2 to the power of M. Because they're the same, I mean, you can use a logarithm for this. Most of the time, you won't need it, but I'm pretty sure you guys all know how to do logarithm. If any of you guys are confused, go ahead and message me in Discord, and I can help you out with that. But yeah, this is, you really don't need to know logarithms for this one. You can see it's 1/2 is equal to 1/2, then M has to be equal to 1 for that to work. Yeah, so from there, M is equal to 1. Now I encourage you to pause and try to solve for N. use experiments 5 and 6 from the original data that we have. So those are the last two at the bottom here. All right, so the answer is n is equal to 1. Hopefully you guys all got that. If you guys are still confused, again, go ahead and message me in Discord and I will probably respond. So here's a variation of the same type of problem that I just covered right before. It's actually pretty easy, but it stumped our class last year when we first saw it. So I'm just going to cover it with you guys. In this case, you have one set of experiments, 1 and 2, that are consistent. That hold one of the reactants constant in both of them, but you have for the other one there is for A, the ammonium, there is no two experiments where ammonium is held constant. In this case, you're going to go ahead and solve for ammonium, so A, just like we did before. With M. So you're going to solve for M just like we did before. M is equal to 1. But now to solve for N, we don't have two experiments where A is held constant. So in this case, we have to use experiments 2 and 6. But instead of just being able to cancel things out, we just have to substitute in M, which we've already solved for, and then solve for N algebraically, as you can see on this thing here. That took me a really long time to write using LaTeX code. So you can go ahead and look at that. It's fairly simple. It's mostly just basic algebra. Let me know if you guys have any questions, again, through Discord. All right, and then the next step here is to solve for K. Remember, K is dependent on temperature, so only solve for K if the temperature, if a specific temperature is given for all of the experiments, and then the question asks for a specific rate law, not just a rate law. From before, we already know that the rate law is rate is equal to K times the concentration of A times the concentration of B, or for this particular example, it's K times the concentration of ammonium times the concentration of nitrite. The specific rate law, you have to solve for K, and it's just going to be inputted right into that equation. The method here is just to plug in numbers from one of the experiments and solve for K. So it's actually pretty simple. Again, it's really just, at this point, it's really just basic algebra. Yeah, you just have to plug in, the data. I did an example with experiment number 1. If you want to get some practice on it, you can go back to one of the other experiments in the slide and you can try it again. But you're going to get the same answer. In this case, it's K is equal to 2.7 times 10 to the power of negative 4. And then K also does actually have units. And just cut and put it in there. Yeah. Right, so now we're going to be talking a little bit about reaction order. Reactions have a thing called reaction order. And this is not about the steps that I've been talking about for quite a while now. Again, that's for like two videos from now. Order is actually just another way of saying like raised to a power. So they're the exponents, m and n. Those are called reaction orders. And then you can think of it kind of like orders of magnitude. That's a good way to remember it. The overall reaction order is m plus n. So for the example we had previously with ammonium and nitrite, the overall reaction order is 2 because m is 1 and n is 1. You may also be asked to find the order of a reaction in relation to a specific reactant. In that case, the answer is just m or n respectively. So basically, like if I were to ask you What is the reaction order in relation to ammonium? And the answer would be 1, which is the M value. You can also have a 0 order, which just means that the given reactant has no effect whatsoever on the reaction rate, and actually won't show up at all on the rate law, because anything to the power of 0 is 1. So reaction order just means, or it indicates how the how rate is affected by each So reaction order indicates how the rate is affected by each reactant concentration. Basically, it's saying that it changes by a factor of the change in concentration to the power of the reaction order. So for first order reactions, that basically just means if you double a reaction, it's going to be a doubled rate. Similarly, tripling the concentration of one of the reactants would cause a threefold increase in rate for any substance that is first order for the reaction. For second order, it actually causes doubling the doubling the concentration would cause the reaction rate to quadruple, because 2 to the power of 2 is 4. And then similarly, tripling the concentration causes a 9-fold increase, because again the concentration is squared. You can also occasionally see third and fourth order reactions, but it's not very common, and basically the only ones you just have to really worry about are 0, first, and second order. Here's a sample problem dealing with that exact thing. It's pretty simple to do, but I encourage you to pause and try to figure it out first. So the answer here is the concentration of H2 is doubled, because H2 is a first order in the rate law. So that's pretty much it for this presentation. Next week we're going to be covering the overall reaction orders and determining a reaction order from graphs. And then of course the week after that we're going to be doing the famed steps that I've been alluding to this entire time. If you're interested in competing, make sure you try the problems that are attached to this presentation. Thank you for listening. Please like the video if you want me to feel good, and have a great rest of your week. All right, so another common question on the multiple choice portion of the AP exam, actually sometimes on the free response as well, is just finding the units of K. K basically just has whatever units we want it to have. It changes based off of the rate law. Remember, the rate is always going to be in terms of molarity, or moles per liter, per unit of time. So the concentration is in, and then also remember that the concentration is always going to be in moles per liter, or molarity. So the way you find the units of K is basically to cancel out the units from the rest of the rate law, and then divide by the unit of time given to you, so that you end up with the molarity divided by unit of time that the rate is going to be in. That probably sounds a little confusing, so here's an example using the same thing that we had before. We have the rate law here, so rate is equal to K times the concentration of ammonia times the concentration of nitrite. Now remember, the units are going to be in molarity per second, and I know that because if you see it in, if you remember from the original chart, the very top of it is going to say observed initial rate, molarity per second. So we know that the rate is all for this entire thing is going to be in molarity per second. Basically, and then you have to find the units of K so that it equals molarity per second. You need to get rid of one of the liters, and then one of the moles, you can kind of see, I expanded it out under like what I wrote units there, and it's basically just what the units of each of the things above is, in the rate law is. So the units of K is liters per mole times seconds. Now obviously in this case we didn't have anything that was squared, but if you come across that, remember that the units, like the units there are also squared, and you'll need to divide by an additional moles or multiply by an additional liters anytime that you see that. If you have any questions on this, it is pretty confusing, so just DM me on Discord.